Locked in a trade fight with Donald Trump, you may have heard that the Carney government is reconsidering its multi-billion-dollar purchase of American F-35 fighter jets.
Canada reviews a deal to buy U.S.-made F-35s. The reason for that review? Trump's trade war on Canada.
U.S. weapons manufacturer Lockheed Martin is reportedly pitching new jobs for Canada. But that offer depends on Ottawa sticking to its plan to buy Lockheed's F-35 fighter jet.
The story of the Saab Gripen has long been defined by restraint. It was conceived as a fighter for nations that needed credible combat power without committing to overwhelming defense budgets. Practicality, efficiency, and adaptability shaped every stage of its development. For years, this identity held firm. Then a series of quiet test results began to challenge assumptions that had gone unexamined for decades. During recent evaluations, analysts noticed anomalies that initially seemed impossible. Infrared signatures were registering far lower than expected, dipping into ranges typically associated with stealth aircraft. Range figures were expanding well beyond what conventional wisdom allowed for a single-engine fighter. At first, these numbers were dismissed as errors. Sensors were recalibrated, trials were repeated, and alternative measurement systems were brought in. The data remained consistent. Something fundamental had changed. What made the shift especially difficult to detect was the absence of any visible trigger. There was no publicized redesign, no dramatic new weapons package, no announcement of a revolutionary propulsion system. On paper, the aircraft looked the same. The explanation lay not in what had been added to the Gripen E, but in what had been quietly reshaped inside it. The force behind this transformation was Rolls-Royce, a company more commonly associated in the public mind with luxury automobiles and commercial aviation than frontline air combat. For most of its service life, the Gripen E had been viewed through a narrow lens. Analysts classified it as a balanced fourth-generation platform, optimized for affordability and ease of maintenance rather than raw dominance. Its strengths were well known: low operating costs, dispersed basing capability, and a flexible mission profile. Yet few believed it belonged anywhere near the SAM category as high-end stealth fighters. That perception remained intact while a far more ambitious effort was unfolding behind closed doors, deliberately shielded from political and media attention. When Swedish engineers began pushing the aircraft to its theoretical limits, they identified an unexpected constraint. The bottleneck was not the airframe, avionics, or weapons integration. It was the engine, not in terms of maximum thrust, but in how heat, airflow, and control logic were managed at extremely fine scales. Replacing the General Electric F-414 outright would have been costly, politically sensitive, and highly visible. Instead, Sweden pursued a subtler option. Rolls-Royce was tasked with reimagining what existed inside the engine rather than altering its outward form. The work focused on internal airflow channels, thermal distribution layers, and the algorithms governing how the engine responds to changing flight conditions. These were not bolt-on upgrades or superficial tweaks. Engineers operated at the level of microtolerances, where fractions of a millimeter and milliseconds of response time determine how an engine behaves under extreme stress. From the outside, nothing appeared different. Official specifications remained unchanged, giving observers little reason to suspect a deeper shift. The decision to keep the program quiet was strategic. Any public acknowledgement would have drawn immediate attention to its implications, particularly its impact on detectability and survivability. By avoiding announcements, Sweden ensured that the aircraft's evolving capabilities would be judged only through operational data, not political narratives. For a time, even NATO planners remained unaware of the full scope of what was taking place. The first clear signal emerged during routine exercises. NATO monitoring systems began flagging infrared readings that defied expectations. Engine heat is one of the most reliable signatures used in modern air combat. Infrared search and track systems and heat-seeking missiles depend on predictable thermal output. The Gripen ES readings, however, showed unusually low concentrations. Analysts initially assumed technical malfunction. Yet repeated measurements across different platforms confirmed the SAM result. Rolls-Royce had fundamentally reworked the engine's thermal routing architecture. Heat was no longer expelled in concentrated patterns. Instead, it was distributed and diffused in ways that reduced the aircraft's infrared visibility across multiple angles. The effect pushed the Gripen E into a thermal performance envelope previously associated almost exclusively with twin-engine stealth aircraft. For a single-engine fighter, this challenged long-held beliefs about what was physically achievable. As confusion gave way to concern, a second layer of transformation became apparent: range. Traditionally, extended reach is achieved through larger fuel loads, additional engines, or external tanks, all of which increase weight and logistical burden. By redesigning internal airflow and optimizing fuel-oxygen mixing under varying conditions, Rolls-Royce enabled the engine to extract significantly more usable energy from each unit of fuel. The resulting increase in range was not marginal. It crossed thresholds that had once required heavier, more complex aircraft. This development carried particular significance for countries operating over vast territories. Canada, frequently cited in internal assessments, faces the challenge of patrolling immense Arctic distances where endurance matters as much as speed. Such missions have historically demanded large aircraft with high acquisition and maintenance costs. With the Gripen ES expanded performance envelope, a lighter and less expensive fighter could now cover comparable distances while retaining agility and lowering operating costs. That shift forced air forces to reconsider long-standing assumptions about fleet composition. The third major change lay in digital engine control. Rolls-Royce introduced advanced adaptive modeling that allowed the engine to adjust thrust output with unprecedented speed. Throttle response became nearly instantaneous, eliminating lag that pilots had traditionally learned to manage during high-stress maneuvers. In simulators and live exercises, experienced pilots reported acceleration behavior that felt unfamiliar, even unsettling. The aircraft could surge forward or disengage with a responsiveness that rivaled larger interceptors. In combat scenarios, this translated directly into tactical advantage. Faster throttle response meant quicker repositioning, more effective threat evasion, and the ability to seize fleeting engagement windows. Opponents accustomed to predictable acceleration profiles found themselves reacting too late. These gains did not require new tactics or extensive retraining. They emerged naturally from the aircraft's altered behavior. Sweden classified the most sensitive details of the upgrade, but enough performance data circulated through NATO channels to trigger internal reassessments. Analysts began revisiting models they had relied on for decades, recalculating threat envelopes and engagement probabilities. The Gripen E, once categorized as a cost-effective alternative, now occupied a far more ambiguous position. It blurred the line between traditional fourth-generation fighters and platforms previously thought to require stealth-centric designs. What NATO initially missed was not a single breakthrough, but the cumulative effect of many small, invisible changes. No dramatic redesign announced the shift. No new silhouette appeared on radar screens. Instead, the aircraft evolved quietly, reshaping its thermal, endurance, and responsiveness characteristics from the inside out. By the time the pattern became clear, the data had already repeated itself too many times to ignore. The transformation of the Gripen E demonstrates how modern air power no longer advances solely through visible leaps. Incremental internal innovations, when applied with precision, can yield results that rival far more expensive programs. How far this evolution can go remains an open question. What is clear is that a fighter once defined by practicality has quietly forced some of the world's most advanced air forces to rethink what practicality can achieve. Tactical doctrines built around predictable acceleration curves and fixed engagement windows quietly began to lose relevance. When viewed as a whole, the reduced infrared signature, extended operational range, and near-instant throttle response transformed the aircraft's survivability profile far beyond its original classification. What made this shift so disruptive was that none of it required altering the engine's external shape. To anyone relying on visual inspections, procurement documents, or published specifications, the aircraft appeared unchanged. That realization marked a turning point for NATO planners. A single-engine fighter had effectively entered a performance tier once reserved for aircraft that cost several times more to acquire, operate, and sustain. Questions followed quickly. Several NATO members requested clarification, triggering closed-door discussions in Brussels. Sweden acknowledged that internal optimizations had been made but avoided technical explanations. Official statements were carefully worded, confirming performance outcomes while offering no insight into how they were achieved. For weeks, the situation remained unresolved. The deeper truth emerged not through formal briefings, but through analytical work conducted quietly inside NATO's technical teams. One analyst began cross-referencing engine vibration data collected during joint exercises with known manufacturing signatures. Every engine produces a distinct vibration pattern shaped by materials, tolerances, and internal geometry. These patterns are subtle but consistent. The data coming from the Gripen E did not match standard F-414 baselines. Instead, they aligned with precision microengineering methods long associated with Rolls-Royce. The correlation was too precise to dismiss as coincidence. It confirmed that Rolls-Royce had been deeply involved in redesigning some of the most sensitive internal components of the engine. That confirmation reframed the entire situation. The Gripen E was no longer viewed simply as an upgraded platform. It became both a strategic opportunity and a strategic concern, particularly for nations with limited defense budgets. It demonstrated that advanced performance no longer required entry into the most expensive tiers of fighter procurement. At the same time, it raised uncomfortable questions for NATO leadership. If such profound upgrades could occur invisibly, traditional monitoring and classification mechanisms were no longer sufficient. Concern grew as analysts explored the broader implications. Internal upgrades leave no obvious trail. They do not appear in satellite imagery, public tenders, or export documentation. They bypass many of the indicators intelligence agencies traditionally rely upon. During private meetings, American officials reportedly described the Gripen E as a strategic wildcard, affordable enough for smaller nations, yet capable enough to challenge heavily defended airspace. It represented a redistribution of air power potential that could alter regional balances without triggering early warning. As NATO's assessment deepened, additional layers of engineering came into focus. One involved airflow pressure modulation at high altitudes. Rolls-Royce had introduced an internal vane system capable of reacting to pressure changes within milliseconds. This allowed the engine to maintain stable thrust while climbing higher and operating more efficiently in thinner air. Pilots noticed the effect immediately. The aircraft felt balanced and responsive at altitudes where performance typically degrades. Interception envelopes expanded, enabling engagements against targets that previously sat beyond reach. Another unexpected dimension was noise reduction, not in the traditional audible sense, but in the disruption of acoustic tracking systems used by autonomous drones. By altering internal component behavior, the engine emitted fewer stable frequency bands. Automated detection platforms struggled to classify the aircraft reliably, reducing its priority within drone-based surveillance and defense grids. In contested environments, this allowed the Gripen E to pass through multiple layers of monitoring without triggering immediate responses. Perhaps the most